So this first one, what would be the central atom? Last two. Carbon. Okay. Is black or yellow easier to read? Yellow? Okay. So we have hydrogen. Okay. We're going to do this two different ways because it depends on how we draw this. We could have hydrogens like this. Or, let me put it up here. We could have hydrogens opposite each other. And this will make a little difference. So carbon has how many valence electrons? Four. Let me change my dot making. Hydrogens each have one. Chlorine?
7.
3, 4, 5, 6, 7. Okay, so we have bonds here and here. So now when we check our polarity,
What are we subtracting from what?
say the carbon-hydrogen bond has what? What's the difference between carbon and hydrogen? 0.9 or 1.9? 0.7? Can someone have a calculator instead of just guessing? 0.35. 0.35. Okay. Carbon and chlorine has what difference? So they are both polar covalent bonds, correct? So now let's draw our arrows towards the more electronegative. For hydrogen and carbon, which one's more negative?
Hydrogen. It's carbon. How do you know that?
It's more it's the larger number on your electronegativity chart. And that means, and chlorine is the more negative, right?
Yeah.
Okay. So there are my arrows for the polar bonds. So overall, is there an overall polarity for this compound?
No.
No? They're both going down or they're both going to the right. So overall, it would be like this, right? So this would be polar. This is polar because there's an overall polarity. Now let's look at, I'm just going to draw these because we know what it should look like. That's a bond. Think about what this is going to look like. Oops. Because we have this going this way, this one going this way, this one going down, and this one going up. What about this one? Yeah, according to that drawing. Nope. Depends on how you draw it. Mm-hmm.
The polar is just has an overall direction.
Mm-hmm. As long as your drawing matches your answer. Okay. Again, then NH3, we have nitrogen, 1, 2, 3, 4, 5 hydrogens. There are polar bonds between nitrogen and hydrogen. Okay. Now, since this is the, what shape is it? No? Yes, trigonal pyramidal. So really we should have, I'm going to just change my bond a little bit. Because they'd be more like this. They're all kind of pointing downward, and then the electrons are on the top. Kind of like this. And then I'm assuming it should be this way, right? Our polar bonds. Which one's polar? The arrows. Yep. So then, do we have an overall polarity? Yeah. Upward. One way you can usually tell if it's going to be polar is One, there's lone electron pairs on the central atom. That will usually make it polar. And if there's different atoms bonded to the central atom, that's when you'll have to check, just like that last one, okay? Okay, questions on the polarity dipole moments? Okay. So there's two approaches to explaining bonding in molecules, and we're going to look at the valence bond theory, and that's where we're going to look at hybridization. We will not go through molecular orbital theory. That's the part in the chapter we're going to skip, okay? So hybridization is part of the valence bond theory, and it's mixing two or more atomic orbitals of similar energies, meaning you have to be in the same main energy level. So 2s and 2p can mix and hybridize, but 1s and 2p cannot because they're not in the same energy level. So here's an example of CH4. When you look, remember our orbital diagrams that we drew with the lines and arrows? And we would fill up the one energy level first. We're going to do the same thing, but when they're hybrid, we're mixing those two orbitals. And so instead of filling up 2s first, we're going to fill all of them as though they're equal energy levels. So let me draw. So this is S, and these were P. So how many, you're looking at the central atom. How many electrons are on the central atom? How many valence electrons? 4. So we're going to fill 1, 2, 3, and 4. Okay, instead of filling the S first and then the P. So a little change because based on what the actual geometries that we already saw with the VSEPR theory, the geometries of the molecule of CH4, by using separate S and P orbitals, they don't get quite the right geometry. So this helps explain that. And when we look at these electrons, they're all they're not a complete filled orbital. So those are the electrons that are going to be available for bonding also. And carbon will form 4 bonds. So we have 4 places where we can share electrons from different atoms. Yes. Okay, and this is called sp3, an sp3 orbital when it's hybridized, because there's an electron in the s and an electron in 3 of the p orbitals. So it's called sp3 hybridization. Mm-hmm. For that one, yep.
Carbon's always going to be
Yep. So remember, this is the s orbital, and these are the p orbitals. When they hybridize, they look more like this. Okay, these are each a sp3 orbital. We have 4 sp3 orbitals, and they each look like this, and they form the tetrahedral shape put together. Do you have a question? Okay. So there's the sp3 orbitals for carbon are the blue, and then the hydrogen, remember hydrogen only has a single s electron, and it's the sphere there. So there's the carbon. Oh, you have water.
I know. I've been drinking it. What?
Okay, now sometimes when we get into the third energy level, there is a d sublevel that gets added. And so we use the d orbital in hybridization to produce an expanded octet. So like the ASF5 that you had on the worksheet would be using the d sublevel in the hybridization. So the first thing you should do is draw a Lewis structure, especially for these ones that can have an expanded octet. Predict the overall arrangement using the VSEPR theory, and then we'll just figure out what the hybridization is of the central atom. So let's look at BeCl2. Beryllium has how many valence electrons? 2. Chlorine has Okay, now what, we need an S. And how many valence electrons? We said 2, so we're going to have 1, 2. So it's an sp hybrid orbital. Yes.
You always have the SP no matter what. You always write SP.
Probably.
This is
Yes.
like
Yeah. Okay, let's try BF3. So boron has how many valence electrons? 1, 2, 3. 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. So what kind of geometry or hybridization would this? Right. Does anyone have a question why it's sp2 instead of sp3? Because boron has 3 valence electrons, so do you understand why we fill it this way? Okay, now there's an electron in the s, and there's an electron in 2 of the p sublevels. So it's where those electrons are in, what orbitals they are. BEH2 will be the same, so let's go to aluminum. Let's go to the PF3. So phosphorus in the center has how many valence electrons? And we have fluorine, 2, 3, 4, 5, 6, 7. Okay, so how many valence electrons? We said 5. So we go 1, 2, 3, 4. Okay, now phosphorus is in the 3rd energy level. So we do have 3D available, but do we want to use it?
No.
Why?
Okay, this is where we will put the 5th electron here at the S because we have a lone pair. So this lone pair corresponds to those 2 electrons. And then these 3 are the electrons that are alone in their orbital. And so they're available for a bond to be formed. So we should have a lone pair and 3 bonds. According to this, it's still a lone pair and 3 bonds. We don't use it. We'll get to one. We'll get to one.
Like, could you not bond something like that?
No, because it has 2 electrons in that orbital already. Is that PBr5, the next one? Is it 5 or 3? 5. We'll see it in the next one.
What if you would do a D though? Like,
We'll get to the next one. We'll have D. What's the name of this hybrid orbital, though? It's still just sp3. You're talking not how many electrons are in the orbital, but how many orbitals are being hybridized. So there's just one s sublevel, or one s orbital still, and then 3 p orbitals. So you'll never have s2, because there's not 2 orbitals in the s sublevel. Okay, the next one's PBr5. So phosphorus we said had 5, but we have 5 bromines. That means it's kind of like that ASF6, where bromine's going to bond to each of these.
You're almost right. Oh, Steve. You were wrong about being right. You're always right. Yes. Thanks.
I need more room. And then I'm going to put D down here. because now phosphorus still only has 5 electrons, but we don't have a lone pair, right? So we have 1, 2, 3, 4, 5. That's where we're going to put it into the D sublevel because we have 5 bonds, actually. We have 5 electrons here available to bond. We have 5 bonds on our Lewis structure, so we need to show those 5 electrons.
Okay, but
So then what would the name of this be? D.
so on the other one, when you had the 2 things on the P, is that saying that like nothing can bond to it? Or couldn't you put something?
Well, but it's already a molecule. It's already done.
But if they're lone, like, can you bond to it?
But they're paired up already.
Okay, so how do you know to go to the D level?
If you have a lone electron pair on the central atom, you want one of them, the arrows, to be paired together in the orbital. So what would SEF6 look like? Selenium has 6. And there's 6 fluorines, which means... Is it okay if I don't put all those dots around the Fs? Okay. Understand. It's understood there are 6 dots around each of those fluorines. So we have S, 1, 2, 3, P.
Okay, do we have to put dots on ours?
Yeah, you don't have to put dots on yours.
Yes, you need dots. Do you want me to go around and put dots around it?
It's only fair.
Okay, how many electrons in the around selenium?
6.
6, 1, 2, 3, 4. Now where's 5 and 6 go?
D.
The D, because there's no lone pairs. We'll do one, just for you. SP3D2, right?
Yep.
Okay, are there any other problems after this? No, okay. Let's do, just for Zach, he had a good question. What if there's 2 lone pairs? Water has 2 lone pairs. So we have, okay, so we need 6, right? We have S, P. We would have 1, 2, 3, 4. Now, do we put it into the D? Right, we have 2 lone pairs, so we need to make 2 of these paired, and that ends up making up our 6. Still SP3.
Is there ever a time where, like, after you fill them all up, you don't fulfill the S goes back to D?
Oh, and skip S?
Yeah.
No.
What about electron delirium if it had 1 lone pair? Would you just do SPE? You'd still go to the D1.
So it was like TeF4. So, okay, I don't know if this is actually a compound, but let's say it looked like this. Where it has 4 bonds and then a lone pair also, because tellurium has 6. Okay, so it'd be S, 1, 2, 3. So we'd have 1, 2, 3, 4. Now we have 1 lone pair, so we'd only put it here, and then, yeah. I don't know if that would ever happen. Because we needed the electrons, we have 4 bonds and a lone pair. So we need 1 paired here for a lone pair, and then we have 4 bonds made. Oh. And this would be SP3D, right? Okay, double and triple bonds. So So we've done all single bonds so far. Not every orbital may hybridize. So, for example, C2H4 has a double bond between the carbons. One of the double bonds will be in the hybrid, and then the other one is not hybridized. So we name this, so carbon, also, we never have done a double two. Okay, let's draw. If you have a molecule that has two central atoms, we really have two central atoms here, right?
Yeah.
We need to tell the geometry around one carbon and geometry around the other carbon. Okay. Also, we're looking at just one of these carbons. So we have S1, 2, 3, P, 1, 2, 3. Okay, now since one of these is a double bond, we're going to cut one of these out. That's an arrow. This is going to be where our double bonded electron, and these three are going to hybridize. So it'd be sp2, and then that's where this 2pz comes in, because this other one that does not hybridize, you would have a 2p, and they use z because remember the p orbital can be on the x, y, or z axes. So that's what the z means. It's on the z axis. So this is your hybrid. Your hybrid orbital is actually just sp2.
So whenever there's a double bond, you just cut one out.
Only one of the bonds. So on a triple bond, only one of them hybridizes. So you have two that,
Cut two out.
yeah.
Would it always be a 2P or like
It's just 2p because carbon is in 2p. If it was like silicon, then it would be 3p. Depends on which main energy level they're in. And so since the sigma bond, a sigma bond is the hybrid bond. So only one in a multiple bond. In a double bond, only one hybridizes, and that's the one that's called a sigma bond. And in the double bond, the second one that does not hybridize is the pi bond. And so in a triple bond, you have one sigma and two pi bonds. So the pi bonds are the unhybridized bonds. The sigma bond, where it says the density between the nuclei, I think there's a picture. Well, actually, let's just look at the picture. It might help. So carbon, this sigma, the symbol is the O with a little line coming off of it. So when you see that, it looks like this. Okay, that's what the sigma right here. And so the sigma bond, the density of electrons, so the electrons are right in between the two carbons. Whereas a pi bond, it gets split on top and bottom of the sigma bond. So this right here is the pi bond. That's what that explanation meant. We have time for a couple, right? Do these two and then we're done. HCN.
Well, let's lunch buddies may be dismissed.
Is that one anyone in here?
I always forget about it.